So, okay, so hopefully you all can hear me in remote. So welcome Jordan and Michael and Shamsa. And go back to this. So I'm recording this. Hopefully everyone is able to, if they needed to, access the video from last time. So if there are any issues accessing it, let me know about that. But I think it looked like some people viewed it. Not that I'm counting, but if you, I put the email I sent you the link, and then I also put it in Blackboard here. So I'll try to, assuming no more technical issues with the cord or anything, I'll try to upload the videos to this playlist, and I'll put it just by like DBA675 and then the date, and so you should be able to view it at a later date. And so I think, it looks like there were 13 views, so some people watched it, so it looks like we we're good for that. So that was helpful, yeah, or at least for the people that were here. Okay, so I'll keep doing that, and it seems like that'll work out for the students who either on a different time zone or need to repeat some of the instructions. Okay, so we're going to go over the homework, or some of the homework that was due today, and how the homework wasn't too bad. No? Yeah. Okay. Um, yeah. So we'll go over it. Uh, yeah, and I'll look through. I didn't look through all your homework yet, but I will. And but the one question helped you, right? Oh, great. Thank you. Okay. Cool. Do you want to be a TA? Just kidding. I don't think that's in the. I don't think that's in the budget. I don't. Yeah. Uh, okay. But yeah, I appreciate it. You guys all working together if you have an issue. Yeah. So let's go over the ones that we didn't do last time. And so it, let's see, week 3, all this stuff. Okay. So last time we did together the movies one and the consumer one, and then we previously did a different one, I think. And then we can kind of look at the other ones. So one of them we didn't finish, but we can go through that one. So I don't think so. So we can finish that one. Yeah. Okay. Um, so we did the MPG one fully, right? We did the we did the consumer one, and we didn't finish the movies one. So why don't we finish the movies one? Okay, and I won't go through the whole thing, but I'll go through the main events. So I did some other stuff here that we're going to do today, but let's not worry about that right now. So for this one, I believe, okay, there's MPG, there's consumer, and there's movies. All right, so we did the R squared. We were about to do the T-stat, and so the T-stat from the output here uh, was 7.69, right? This part. So if the T-stat was 7.69, we would look at the T table. Let me just pull up we have two Shamses. So that's a mixture. Okay, so we look at the T table on the other section here and look that since we have 98 degrees of freedom, and we want to look at 95% significance, so 98 degrees of freedom would bring us to about here. And so the critical T would be 1.990, right? 1.990. Sure. Yeah, it's the same. It's not gonna make a difference. It's just they do like a cutoff. Yeah, that one's fine too. It's close enough. So 1.990, since this is bigger than 1.990, we can go ahead and confirm that this same statement. Not the household size, the number of theaters variable is significant at 95% level. Okay. Then we would interpret the coefficient, which is 0.10, right? What was my format here? Kind of like this. Okay, coefficient is 0.10. Okay, and this has to do with the relationship that we predicted between number of theaters and total gross sales in millions, right? So here, you would do something like we're looking at when this goes up by 1, what happens to this, and make sure you keep track of the exact problem you're looking at and the notation or the units, sorry. So basically, if the number of theaters that the movie was shown in increases by 1 theater, then the estimated effect on the sales was that total gross sales would increase by 0. Oops, sorry, 0.10 million. And we could, so 0.10 million is what, 100,000, right? There you go. So basically, each theater increases revenue by about 100,000, correct? Yes.
So I didn't have the I didn't have the money.
But you had the 0.10
Yeah,
million? Yeah, that's correct.
Yeah. I took 0.9.
Uh, oh, I see. You rounded out more. That's fine. Yeah, that works. Yeah, you can round. It's about the same thing, right? Yeah. So basically, like, you can leave it in the full units, but it's easier to translate if you make it into like 0.1 millions, right? So if the number of theaters that the movie was shown in increases by 1 theater, so 1 more theater that we get the movie showing in, then the estimated effect on sales was that total gross sales would increase by 0.10 million, or the same thing as 100,000. Okay. All right. That was that's what we all got pretty much. Okay. And don't worry if you just put 0.10 million, but just make sure the units are correct. Or the yeah. Okay. So good on that one? Yeah. Okay. What? Oh, okay. So yeah, that's the thing. It's like examples. What did you say? You don't have to. You don't have to read it out loud. Then.
I don't know, like, I think for me, the struggle is just like when it comes to like interpreting the data. So I just base it off the graph, like the total, and now that I'm reading it, like, it doesn't make sense, but I just basically put if the total gross sales increases by 1 million, then expect the effect on the number of theaters increases by 0. So now that I'm looking at it, I'm like, yeah.
Yeah. So I no, that's why we're practicing. So yeah, I think it's good to just kind of start with like the next couple I'll do. I'll put like a general statement, and then we can modify it based on the variable definitions. So yeah, that's a. It usually takes a few. Um, it's not you're not the only one that had a creative answer. Um, so let's do the other one. I won't do the full thing, but I'll do. I think everyone's good on part A and part B. It seems like, right? And part C and part D are uh, the more challenging parts. So we'll do those for the others. But any, everyone's, yeah, let's move on for this one. Okay, and then later we're going to, I'm going to show you, if you did some of the readings, I'm going to show you how to calculate some of those statistics in Excel, and that you can kind of see, get an idea of where they come from. You won't have to do this every time, but just it's important to kind of see how you can calculate those coefficients and R squareds manually. Um, but most output or software programs do it for you, but the kind of the backbone behind it is important, right? So we'll do that in a bit. All right. Now, why don't we do, just make sure there's no questions here. I'm still recording. Yeah. Okay, so we did consumer. We did MPG. We didn't do snow, right? Let's do snow. Okay, so I guess it kind of depended on what variable you looked at as y and what was x, but I think the common example was to try to predict snowfall with temperature. So the temperature was in my analysis the x variable. It's okay if you did it the other way, but as long as you fully interpreted it, and then snowfall would be the y variable. So you're basically trying to predict snowfall with weather. And the hypothesis would be that when it gets colder, you probably see more snow, right? Or at least that's what I would think. Okay, and this is by city and state, so we get no snow, obviously, in San Diego, and San Francisco and San Jose. Okay, probably because the low temperatures, like that can't be right, right? Average low temperature. Okay, it still seems low, right? It's 58. Average low? Yeah, in San Diego. Yeah. Well, that's what I mean. Like, doesn't that seem low or high? I mean. Well, it says average low temp, so I think that means for one year they averaged all the low temps But that also includes like the low temps in like July, so maybe that's the, okay. But the point is like, all the California cities have no snow. Or obviously it doesn't snow in Phoenix, I don't think. Doesn't, LA, no snow. Uh, it snowed here like last year, right? A little bit. Yeah, did it? Yeah, every once in a while, but yeah,
It's a dusting.
it's, yeah, right. Okay, so I will do the data, data solver. Yep, do that. Data analysis, regression. Okay, so Y range is the average snowfall. X range is the low temp. Just click on the labels and hit OK. All right, and then I'll just do like a rounding off because this is, so we can do, so, and you didn't have to do this, just, it's, if you want to simplify the decimals, it's, I like to do it. Um, okay, so we'll just look at the coefficient for average low temp, and we'll also look at the t-stat. And even though it's negative, you think of it the same way because that's just the direction of the graph. Okay, so the 7.74, we would look and compare to, maybe I can pull this up at the same time. We can do it that way. Whoops. All right. So 49 is about here. If you did this 61, that's okay. But 40 degrees of freedom, 95% significance would be 2.021, which is, it's bigger than that. And so that's significant, right? So this, your critical T for this one would be about, and they're all about 2. So really, if you use 2 as a rule of thumb, you're probably good to go. But just if you want to get in the weeds, technically it would be 2.021. Yeah. So that one's significant. And I'll write out the last part because that's the main event. Okay. So we just want to do this part. Okay. This one is the snow. Call this number 4. Okay, so we'll just do part D. So the coefficient is negative 2.33. Okay. So before I do this part, I'll kind of start with a general statement. So I guess it helps to know what the variables are. So it looks like the y variable is average snowfall. Uh, I guess it didn't really specify what the number meant. That could be like inches per something. So you don't have to specify it, but I'll leave it at that for now. So just average snowfall, inches.
Yeah.
Yeah.
I went back for a couple minutes.
Yeah, so either one's fine because it didn't really specify that the snowfall, but I'll just say it's in inches. Snowball? Oh, uh, yeah, and then this is average low temp in degrees. Huh? Yeah, that's okay because it didn't specify, but I'm just so you know what the interpretation is. Uh, so yeah, got it. Okay, so Y is average snowfall, and let's just say it's in inches, and X is average snowfall in, sorry, average low temp in degrees. So what this 2.33 would mean is that on average, when the temp dropped by 1 degree, the expected, um, sorry, that's not what I meant to say. Well, I guess I could say it like
Increase by one.
that. Yeah, technically it's that would, it just, okay, we'll do it that way. Yeah, yeah. So I'll do both. So when the temp increased by 1 degree, uh, the the expected result was 2 point, or yeah, 2.33 less inches of snowfall.
Yeah.
Okay, or you could say, I think it makes more um, translationable sense. No, that does make sense. Or you could say um, when the temp fell by 1 degree, uh, the expectation was a increase in snowfall. Yeah, of 2.33 inch. Either one is fine.
Basically wrote everything. The very first step.
Yeah,
If the average low temperature increases by one, the expected average fell,
Yeah.
which is all different ways.
Yeah.
Say that.
no, that's right. Just like if you were going to put this result in like on the news, they'd probably do it like this, right? They'd probably say like when it gets colder, snow goes up. They wouldn't say when it gets hotter, we get less snow. But they're the same thing. You both are right. So something like on average, when the temp increased by 1 degree, the expected result was 2.33 less inches of snowfall, or when the temp fell by 1 degree, the expectation was an increase in snowfall of 2.33 inches. So basically, each degree cooler, you get 2.33 more expected snowfall in inches. Yep. Okay. Okay. Right. How about the other one? Okay. So consumer, we didn't do smoke detectors, right? Okay. So this one, probably the most obvious. We were trying to predict. We were hoping to see most more smoke detectors would decrease the chance of death. So if a house has more, if more houses have smoke detectors, you would hope that there'd be less deaths because they're causing awareness and stuff like that. So this would be uh, X, sorry, and this would be Y. Okay? And if we did this, okay, we get something like this. Okay, where our coefficient is negative 32. And so this one has even a different, I'm going to interpret this one, and it's okay if you didn't word it exactly the same because it has to do with percents. So it's a little bit trickier, but um, yeah. So the t-stat is, the table is going to be something like, well, this one's only 15. So as long as our t-stat is, oh, here's 15. So is our t-stat bigger than 2.131? And without the negative, it is. So that one's significant, right? Which one? It doesn't make it shouldn't make a difference. Yeah. Okay. Yeah. And then if we interpret this as we've been, we know that, well, let's define the variables first. So this is, oh, it tells you. So this one tells you exactly what you're looking at. So this is the percentage of homes with smoke detectors, and this is the home fire deaths per million of population. So both kind of unaverage metrics, but let me try to interpret it and we can go from there. So, okay, 5, let's call this smoke detectors. Okay, so again, we're quantifying the coefficient, or we're writing the coefficient plus interpreting it, and this is exactly the linear effect of x on y. In this case, the coefficient is negative 32.76. Okay, and the variables are y is home fire deaths per million of population, x is percentage of homes with smoke detectors. Okay, now, what does this mean? So we probably got something like this, but I'm going to try to stick with the units. So when now you, it's okay if you didn't get this exactly because if you notice here, um, the percentages are in decimals, and so that means an increase in one is like 100%, just the way it's written. So if this goes up by one, like because that's 50%, 0.5, and that's 74%. So the way we're interpreting a 1 unit change in this context would be 1.00, which is 100%, which essentially means it doubles. So let me write that out and then so when the percentage of homes with smoke detectors increases by one, right? One, which in this case, in decimal terms, is 100%. Then the x estimated effect is that home fire caused deaths will fall by 32.76 per million of the population. Okay, so if you didn't get the exact wording, it's okay as long as you kind of understand the outcome here. So I'll write it in a more, this 100% increase is a bit misleading because if you listen to like a podcast or you hear something that's like this went up by 400%, that just means it went up by 4 times. So it's a bit misleading to do percents when it gets that high. And so I think it's more clear to just say when the number percent of homes with smoke detectors doubles, then you get this. So you could also write when the number of homes with smoke detectors doubles. Okay, sorry. So 100% is just times 2. Then we'd expect to see 3.76, sorry, 32.76 fewer deaths per million. Okay, so let's get that again. So when the percentage of homes with smoke detectors increases by 1 or 100%, then the estimated effect is that home fire caused deaths will fall by 32.76 per million of the population, or when the number of homes with smoke detectors doubles, then we'd expect to see 3.76 fewer deaths per million. And so that means like in a random sample of homes, that there'd be 3.76 fewer deaths in that million, the million people sample. Yes.
Where I get confused,
Yeah.
like when you have to write the ratio, like I get the numbers right, like 70.70.
Yeah.
This is, I get them all, but when it comes to that part, right, then it's the very confusing. This one specifically is different about.
This one's a bit tricky, but so yeah, that's why we're going through them for examples to like knowing the sign of the relationship is good, but knowing exactly what it means is also important because if you just see the negative 32, it's important to know what it means in the context. So in the context, if this is true, it would mean if we double the homes with smoke detectors, we'd lower about 33 deaths in a sample of a million people. And the reason they do it per million is because if they didn't, it would be like 0.000032 deaths or something, right? That it's broken down in a scale that's more readable. Like for example, let me show you what I mean. So let's see if there's any questions. If I were to look at like um, death rates, not to be, normally like the CDC has pretty accurate readings for this. So you'll see that see how they standardize it, and that's because if you don't, it's very hard to come across the decimal. So it'll say like something like the age-adjusted death rate increased 5.3% from this deaths per 100,000. So they're putting it per 100,000 because if they didn't, they'd say deaths increased 0.000835. And so it makes more sense to standardize the variable like that. And so that's why they're doing it like per million because here, infant mortality was this many deaths per 100,000. Okay, so it's just a standardized way of making it more clear and compare it. And that way, like, if let's say you work for I don't know, let's say you work for one of these organizations, like either you manufacture smoke detectors, you work for the fire department, and you're looking for some result, and you see something like this. Let's say that one year it's like 3.76 per million, and let's say there's a new study, and you're hoping that number goes up to like, or sorry, goes down, or sorry, up, so to like 50 per million. So if you're looking for um, like a target result, then you might want to focus on like the number, like the coefficient. And so, for example, if you're familiar with this, number per million, then if you saw next year it went up to 50, then that means you got fewer 50 deaths. So that's why it's like that. But if you didn't write it exactly like this, it's okay. Yeah. Well, that's where we're going. Well, I mean, okay. Well, you can, you know, make some last minute changes if you so. You did? Okay.
Yeah,
Uh,
that's what I mean. I knew when we were doing this one, that there was probably like,
Yeah.
weighted by, I said 1%, but then, because I didn't know, it was like, we had never covered something where it increased by 100%.
Yeah.
So that's why I was like, it has to be 1% to make sense. Then when you look at it, it's like 32 is what we, that's where the intercept is, so it's like, I have to go from 0 to 100 to do that. So it makes sense, like, when you, like, writing it up, my numbers are the same, but I said. This is a little bit, oh, yeah. But I don't care.
Yeah. 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 Right. Yeah. This one is the trickiest one so far. It's like it took me a second to figure out. But
Because there's still all thin decimal percentage,
mhm.
but it's still over the course of it. What's this like? There still are increases that are actually 1%. Increase from like 17%. It fell by.
Oh,
Like,
yeah.
why isn't it?
Well, it's because the way you measure this kind of regression is this is a 1 unit change, and this 1 unit change is translated into. Now you could you could also do this if you wanted to and make it easier, or I don't know if this is easier or not, but I could just say this equals. So now they're all in percent terms, and I could run the thing again and just assume, and then it would be the same, but the effect's going to be multiplied by 0.10 by 100 because now they're in percents, not decimals. See what I mean? So it might be easier for you, or if you wanted to present this or translate it, uh, if this is just in percents, like that's now 50%. That's now 67%.
So it's gonna be the same when it's not gonna be, like, the coefficient will be the same, so it's still regardless, be over 100.
No, now if I did it, it would be if this goes up by 1% because it's in percents.
So the actual
Yeah,
coefficient.
the coefficient would be different.
Okay, exactly. That's
Yeah.
like kind of like what I was,
Yeah.
in
So
my mind, like what I was. Different, but it's the first.
I know that. So it's yeah,
From the whole 100%.
yeah. So watch if I do it again. See?
Yeah.
Now instead of -32, it's negative 0.32. So it's the same exact mathematical effect. It's just which way do you want to look at it. So I don't know if this is easier to the translator this, but this way it's in one is 1%, and this way it's in one is 1.00 100%.
100. Yeah, see, that's like,
Yeah.
for analyzing it the way we have been, the other way.
So either one is correct, but yeah, it's just that's why it's very important to pay attention to the like what they're measuring. Yeah, but that one is it's kind of confusing, I think. But yeah, good. Okay, we have one more. And if that one probably not too many issues. What was I looking at? Oh yeah. So NFL. Okay, sorry. Okay, so this one we're looking at um, revenue and current value. So I think the way I usually look at this one is we're trying to predict the current value with the revenue, right? So revenue was the X variable, and current value was the Y variable, right? Yeah, that's okay. Um, and I'm not sure what year this is from. Obviously, it's a little outdated because Washington is now the Commanders, not this canceled version. Uh, so I think all the other teams are this. Yeah, yeah. Well, it just based on which what you want to predict. So you could go either way, but usually like it, the research question is like this one is the way I usually have it is that the y variable is second, just so it's easier to do the graph.
The way
Yeah,
it's doing it,
yeah,
current
yeah. But you could go the other way if you want. It's just this. I think when you look at this, the standard I or the standard uh, project would be to predict this with this. But you could go the other way. It's still right.
so both ways are gonna be right.
Yeah,
Yeah, because it's ideally the same. Coefficient.
yeah.
That's one thing I did. Square and use that, like,
Right.
it's just coefficient. So
Yeah.
it's
Yeah, it's the same thing. Yeah. It's just, okay. So, and you'll notice here that I'm not going to graph, well, maybe I will graph it, but I just wanted to graph it real quick because you can see that it's a pretty strong relationship, but there's one team, it's the Cowboys, that is way out. So that's the one that's, you know, not value wise, but maybe, you know,
I want to like,
y-
I
y-
guess,
I think they might be the highest in the US, if I'm not mistaken, but I'm not sure. Yeah. Yeah. Fan anxiety might be up for what's happened, but not the value of the team. So they're like 500 million compared to most of the other teams that are about 250. And thus their current revenue is also higher. So they're a bit of an outlier, but it seems like they're on the trend. And then like where are we? That's the Patriots. Who's the worst one? Or 229. The Raiders? No, it is. Yeah. That makes sense. This is probably before this is before they moved, right? So that does make sense because, uh, but you can, yeah. Oh, this is old. This is St. Louis Rams. Okay. So if we did this one, uh, yeah, LA Chargers. Okay. Okay. Hello. Right. Yeah, we will have to check like after the spring break because there's all the classes that go on the quarter system. It's possible there's a class in here after spring break, so we'll have to double check. But
Yeah.
yeah, if so, then whatever. So yeah, because the quarter system goes one more week.
We'll just get it.
Or no, it's yeah. You can just put a chair in the door.
We have guest students coming like for the meals.
Yeah, you're welcome to bring donuts, and then yeah. All right, last one I think is the NFL one. Okay, so the coefficient here is 5.01. And in this case, y is the current value right here. Oh, you did the other direction. That's fine. You can do that way too. Yeah. Yeah, it's fine. So the current, all right, yeah. So current value is dollars in millions. And the Y value is, sorry, the X value is revenue in dollars, millions of dollars. Okay. So this one should be, so when the revenue of the team increased by 1 million, right? The expected result was an increase in current team value of 5 million. That's it. Or the other way around. Okay, when the revenue of the team increased by $1 million, the expected result was an increase in current team value of a 5 million. So basically, what this would say is each time they make $1 million, the value of the team goes up by 5 million. Seems a bit unlikely, but that's what it says. So that one's pretty.
Yeah.
The other way would be, um,
The way you, like, the way I have it, like, so I did current values at Y.
mhm.
The,
So I think you're that way.
I wrote
It would be this goes up
I
by
just read it right now. I'm pretty happy.
yeah.
Yeah, you could, I wrote something. We'll see. If it's the same. But I wrote it, saying like, I wrote it like you wrote it, but I might not.
Okay,
But
that's all right. Okay, so that's all of them. Makes sense? Yeah, dude.
when you make it happen, it makes sense.
Yeah.
Right? And then, yeah,
Which-
I don't want to.
But you make it look easy.
Well, you just gotta follow the format, and like if you just first you gotta write out what the variables are, and then you know like if x goes up by 1, y goes down.
Everything's good. The numbers, everything except for that.
Yeah. But well, that's why I went over it. So I can. Do you want me to give you everybody like a time to revise it, or do you want me to just agree it? Want to revise it? You already printed it out, so I don't want to.
I'm just annoyed at myself.
Yeah.
I did it the way you did, but then I switched the graphics from my phone like that. I just
Yeah.
switched it. Like, I understand. Making mistakes. I don't know how to fix it. I did it internally. Everything right.
Yeah, you can have you can do a revision if you want. Technically I didn't say it was due until today, so you can have until midnight today if you want to make some slight adjustments. But I won't. If you didn't write exactly like this, I'm not gonna. Yep, okay. Okay. Yeah. Okay. Uh, yeah. All right. Let's.
And also, I read you article.
Oh, good.
Except one of them I have really hard time is that book one.
The book one? Oh, the.
The version one at the end of the this all the calculations, like the example,
Yeah.
that oh yeah. Anyway, so besides that, everything else is cool except for that part.
Okay. We'll wait for Brian to get back. I guess we could take it. Yeah. Do we need a break, or do you want to keep going? All right. Yeah, Brian just took a break, so we'll take a 5-minute break. That makes you sleepy? Yeah. Yeah, Brian, I said that the class could make some revisions if they want.
Oh,
So-
no, I.
So if you want to, well, yeah.
Yeah,
You have until midnight to make revisions.
Okay,
Up to you.
okay, got it. We'll
Yeah.
do that.
Just don't do it while you're driving home.
Yeah.
Yeah, yeah, sure.
This, see, number one where it has right, that's correct. You have to put it there. So number one where it is increase by 32 for the increase by 100%. No, I think it's 5 even.
It was by the third, it was decreased by 32% of the position. And the percentage of
You'll see the number of homes. By the increase by 32.75. When the percentage of homes is not affected, yeah. I just wrote, because I wrote the 1.0. You expect that, that's right. Yeah. No. So, if the number of sales, so if sales increased by 1 million, expected effect would be the current value of the is the people, the coefficient 4.5, and is that the other way around? Yeah, it is, it's both, it could be 0.19. Yeah. What do you have written? Well, you just said you both the other. Because if you think about it, it's the same thing. One increases by $1 million. It's 1/5. That's basically that. Flip it. If the revenue of millions increases by 1 million, bank on current value increases by 5 million. The other current value increases by 0.19. Whatever it is. Or like, yeah. He wants to understand who's making this easy. But once you don't understand, it's confusing.
Yeah. Well, then
What is this showing that? Oh, that is.
Just need some changes in my wording to make. I'll check, I'll double check and recheck.
okay.
Yeah.
Thank you. Change it. No, no, no.
It's probably.
Well, it's snowball, you would get more snowballs, so I find it balanced.
Lloyd's Bobby. Yeah, and people go to coffee loading here.
Huh?
He's like, no.
Oh, well, it's tea, so.
Black tea.
No, it's like spearmint tea or something. Yeah, I'm trying to cut back on a little bit of coffee first. So,
See what I thought about.
so now I just have a pot of coffee in the morning, and then move on to tea.
That was a second.
So I take 4 cups of coffee and then I do want to take 5 minutes because I'm part of that. So I do tea at the end and then I slept for 3.5 hours. One.
That was when I was paper before 5.
No, I was.
Then you just wanted to finish that French, bring the door. Right.
Of course.
That's all I'm here.
You mean my work for me?
Yeah. All right, should we keep going here? All right, so let's get to the stuff I had for today, which isn't. So what did I post? Something. Okay, so for today, I just posted a few things. So no homework due today, but you can revise that one. And then, sure, you got it. I won't grade them today, so no. All right, and then next week, I think we'll start looking at multiple regression. So we're going to add some things. Okay, but if you looked at some of the readings, I just put some things that I thought were important or memorable, and then we'll do some of the steps. So this is under um, week 4, and there's just one Word document. Oops. Okay, so the first one, which was the intro to linear regression, so there was this one. Which gave you a nice example, I thought, and then we'll manually calculate the coefficient and the intercept based on this reading. So, so by far the most commonly used criterion for the best fitting line is the line that minimizes the sum of the squared errors a prediction, that's what we're doing. So we're minimizing the sum of the squared errors to fit the line through the data points. And we're going to calculate the slope in a minute, or maybe right now. So you can calculate the slope, which is b or beta, whatever you want to call it, by looking at the correlation coefficient and then the ratio of the standard errors, or the not the standard errors, the standard deviations. And then you can get the intercept by looking at the mean minus the coefficient times the other mean. And so I'm going to show you how to manually do this in Excel. You don't have to turn this in. I just want you to understand the backbone of how the betas come from and the intercepts come from. So what we're going to do, if you want to follow along, is look at some of the examples, calculate the um, correlation, which we did before, calculate the standard deviation, and then you can get these. You should get the same estimates you got from the output of the software, right? So if we look at any of these, okay. Um, okay. Do we, anybody have a preference of which one I do first? Or I'm not gonna do them all, but I'll do at least, which one do we like the best?
You the one, you the percent.
The hardest one?
Yeah.
Okay. That was the smoke detectors. Okay. All right. So I'm gonna get rid of this part because it's gonna mess up our interpretation.
Real quick, in the future, if we do have a percent problem, we can calculate it where
Yeah, yeah,
it'll be so.
yeah,
Because it is easier to.
yeah. Actually, I'll leave it and I'll do it both. So we'll call this either one of these is X, but you can only choose one or the other. All right. So what we're gonna do is use this simple formula, which is beta, or the coefficient is the correlation coefficient times the standard deviation of y divided by the standard deviation of x. So the the magic coefficient that comes out is just based on this. So it's just based on the correlation between the two, which is obviously not going to help because if there's a correlation, there's a better fit. And it's based on how the standard deviation of both, which is the spread from the mean. R is the correlation coefficient. Coefficient? Or just the correlate? Yeah, just the correlation. Okay, and then I even have then we can even calculate the standard deviation manually in a minute, but we'll start with this first. So why don't we look, I'm just going to copy and paste this, and we'll follow these steps. Oops. Okay, so that's the formula for beta, or the coefficient, and this is the formula for um, the intercept. And we should get the same result. Okay. So we need to get the correlation, the standard deviation, and then the means. So R, or little r, is the correlation. So to get the correlation, we did this like day one. You can just do equals correlation, or CORREL, and the correlation between this x, comma, this y. Okay.
I'm putting this time when you do installation, I will include of everything, only including two. I mean, before you include everything.
Oh yeah. So well, this one because yeah, good question because the titles are here. But the reason I chose the titles in the regression is because it gives you like a little report, and the report has a title of the variable. And so that's why this one you don't have to because, or this one you shouldn't because that's not a variable. Yeah. So yeah, good question. So there's the correlation about -1, so it's a pretty high correlation, right?
Real quick again,
No, the formula is equals correlation of this and this. Yeah. Okay. Uh, and then we also, you need help?
I just, my computer's being slow right now, so I need to catch up with this.
Okay. Yeah, we'll do another example. You don't have to turn this in, but I'm just,
No,
yeah. But, okay, so we've got the correlation. We also want the standard deviation. So I'll call this SY for the standard deviation of Y and SX for the standard deviation of X. So the standard deviation, there's a formula for that. And in H2, you can do equals STDE. See, there's a bunch of them, but you want the one that says sample because you're only calculating for this sample. So STDEV.S is the right one. Oh, yeah, oh, sorry. Yeah, I'm recording.
No, you won't, everyone else will.
Yeah. Do you have the, yeah, do you have the password? Do you have the password? Okay. We could all, yeah, is that better?
It's not that.
Yeah.
Not like.
No, it's, we could all, yeah, we can rearrange the tables at some point if it's easier, but
Yeah, no, this sounds about.
okay. So the standard deviation of Y is the standard deviation of the Y range. So in H2, you can do equals STDEV, and if you double click the one you want, STDEV.S, standard deviation of a sample. And if you just choose the Y range, which is C2 to C18, there's the standard deviation of Y. Okay, and then the standard deviation of X would be done in the same way for the X range, equals STDEV dot S, and then in the argument B2 to B18. Okay, so thus far we just have, we use three simple formulas to get the correlation. Yeah, you probably just need to increase the decimals or something.
I think use the reduce.
Oh, you-
Use the whole thing. There's two different X variables within one percentage.
Oh, yeah.
That's my X. That's my.
So,
I'm right at there. I'm using. the percentage.
Okay, so this one in G2, it's equals the, here's the formula, equals CORREL, and then the X range, comma the Y range, like that. Or you can see it like A2 to A18. Yeah, yeah, because it's the correlation between the two. Yeah. I will say you messed up. Yeah. Okay. So you should get like negative 0.9. All right. And then the standard deviation of Y is this formula, equals STDEV.S. And then in the argument, just put the C range, the Y range. Okay.
Just, I'll get with you after this.
All right. All right. And then in the I, and for the S standard deviation of X, it's equals STDEV.S. And then the, oh, did I choose the wrong? I did. Oh. Sorry. So equals STDV in the A range because that's what I used for this one, right? Yeah. Okay. So that's that would have been wrong. Or wouldn't have got the right coefficient. Okay, so we calculated the correlation coefficient, the standard deviation of y, and the standard deviation of x. We're doing this one and this one for now. Okay, then we can use this formula to get the coefficient, and it should be the same as the one we got from the report. So let's hope that that comes out. Let's see. So beta here in E, you can do equals. So I'm going to follow this formula. So equals R, which is G2, times parentheses SY, which is H2, divided by SX, which is I2. So we calculated these things, and now we're just plugging them in the formula. So enter. So that should be the same thing. Negative 32. Oh yeah, sorry. This one?
Was it divided by?
Minus.
Yeah.
Was it negative 32?
Yep, that's it. Yeah, it should be exactly the same as this one. 32.76. Yeah, right? Well, this is the manual way to do it. The way we just did it is manual, but I'm showing you the math behind it. Yeah. So this is the coefficient you've been talking about. If you want to calculate it just in Excel, that's how you do it. Well, I thought you wanted to know the basics. That's a base. That's yeah. Okay. I'll just clean up my decimals so I can. All right. I don't know. No, I do know it's for like growth rates. You don't want to use that unless you're looking at growth rates. There's different types of means. Yeah.
I forgot.
It's the correlation between x and yeah. Yeah.
Noted. Following along with beautiful.
Yeah, that's the idea is yeah. If it,
You're just like looking at it. Just like watching it. It's not thinking.
I know it helps to do it with yeah. I agree. I couldn't learn it if I didn't do it myself either. I, if you just watch someone do like a PowerPoint,
Yeah.
yeah, it's fun, right?
You want to know.
Stats, yeah. Regression is fun. That's the hard part, yeah. That's the whole point of it, though. That's
Negative. The increase what decrease. What it goes.
Value when we're leaving physical.
yes. The t
We don't take the absolute.
not in the coefficient. You leave the negative. Yeah. Yeah, because that's the direction. That's the way that the effect goes. The t stat. You take away. Yeah.
we're having a big party. Big party.
We're having a big party?
Yeah.
Are you saying, maybe
Yeah.
A donut party?
I mean, with the what do you call it? With the shish kebab, chicken shish kebab,
all of that to get the,
palau.
but that's just like.
But I-
Okay, yeah,
And now you have.
yeah. All right, so now, we can calculate the intercept too, right, with this formula. So we need to get this is just the average of y and the average of x, and the rest of it is just the formula. So let's call my the mean of y, which is just equal to the average of the y range. Average of C2 to C18 should be there. And then mx is the average of x, which is equal to the average of the x range, which is A2 to A18. Okay? So then we can get the intercept from this formula. So in F2, you can do equals my, which is J2, minus parentheses B, which is this one, E2, times mx, which is K2. So the formula from the text, A equals my minus B times mx, there it is, and that should be our intercept. 4.66, 4.66, right? And that should be the exact same thing we got here. Yes, this one?
One second, so from two all the way down.
Uh, what's the question?
B equal to R, that one equal to compare when you get from the previous.
Oh no, oh this we just calculated B.
Or from the previous, right?
Yeah, yeah, right. Yeah, for the previous, right.
R and F Y would be this, right?
Well, we did those. We calculated those previously. Yeah, sure.
I'm getting like.
Yeah. Basically that.
Yeah.
Why, we gotta think about. Wherever you.
There we go. Okay, and then we'll do it for the other, this one as well. Oh, it's keeps going. There it is. Yeah.
And then do the same thing.
And then this is, they should be the same. Yeah. So we got the same things, right?
Yeah.
Yeah.
Yeah, the different formula is the well, and then I looked at the equation. Well, sure. Minus and those e is the whole like
Yeah. Right.
right.
This one?
There's a minus before the parentheses.
Is minus oh,
So it's J2 minus, and then the parentheses, E2.
oh,
So those are the kind of words.
oh, it's
So those are the cells.
eight minus right. Your R value. And then then
I'm only concerned with those. Not with proper operation. That's the parentheses on spot.
Yeah, that's why you gotta.
I kept putting a reference to those, I see wrong in the thing. Wanted to do everything together.
because our wrong.
Oh yeah. Yeah.
Face value.
Okay.
I was like, ours are.
Well, right now I teach another class, the data analytics class, right next door before your class. But I've taught like, well, I'm economics, so I used to teach a bunch of like undergrad econ, but it kind of conflicts with my work schedule now. So usually the undergrad classes are during the week, so it depends on when for work. I go to Irwindale, yeah, but the main office is in Roseby. Yeah, Irwindale's just that way, like 10 miles. Okay, all right. So why don't we calculate um, the same thing for the other x? Yeah, let's see if we get the same result. So we're just going to do the same thing. R is now the correlation between this x, yeah, and then this y. Yeah.
I was gonna say, I thought you did like a nice little. Get like multiplied by 100. So I did like a quick little.
Oh, yeah. Okay, good question.
That's just what I felt.
Well, no, no, so what I did here is just A2 times 100 gives it to us in percentages, like percentage. And if you just, Excel knows usually what you're trying to do. And so if you take this argument and double click the bottom right corner like this, see that little X?
I did that, but he made it all fixed.
No, it shouldn't.
I think I made it. So
What?
usually
Yeah, so it's equals A2 times 100. And then, so don't see this like little box right there? Like double click it like that.
double click.
There you go, yeah.
I would drag it. That's why I was like. I feel
Right.
like
So that applies the same formula down. See, this one's now getting multiplied. They're all getting multiplied.
Yeah, yeah.
Yeah. So then the correlation is the correlation between the original y and then the new x with the percentages. So remember now this is the actual percentage. That's like 50%, 67%. Okay, then the standard deviation of y should be the same, but you can, I'll just say equals, we can do it again, I guess. STDEV dot S of the y range, which should be exactly what we got before, 4.53. This should be a little bit different because we're using a times 10 times 100 situation. So it's probably going to be, well, let's do it, equals STDEV dot S for the new X range, B2 to B18. Much bigger because now they're bigger units. And then the mean of Y should be the same, equals average of C2 to C18. And then the mean of X is now the average, oops, of this range, B2 to B18. Okay, so we did these same exact variables for the new X range.
Question. The 91, the pollution, which one you get? The rate, how do you get it? 91? The father. Yeah, 91. How do you get the one?
Equals the correlation between X and Y.
The same thing?
It should be the same because you're just changing the units, right?
Okay.
Yeah. So you just, it should be exactly the same, which it is, right? Yeah. It's the same graph, you're just changing the notation, or you're moving the decimal. Okay, then if we were to do the beta, or the coefficient, we're following this formula, right? So in E7, it's equals, I don't know why that's red, 0.91 times parentheses new sy divided by new sx parentheses. So equals G7 times parentheses H7 divided by I7. And negative 0.33. That's it, right? Okay, and then if we did the intercept, it would be equals average y, J7 minus parentheses, beta, which we just got, E7 times mx. Okay, equals J7 minus E7 times K7. And if we were to compare that to the chart, which I'll standardize here, do we get the same thing?
Okay, Jay.
Justice. Yeah, same thing, right? So now you can see kind of the you could do it manually if you wanted to. It just takes a bit longer. But that's where it's not magic. It just comes from these. Yeah,
When you get the qualification, the qualification,
that's the definition of beta using the correlation coefficient and the ratio of the standard errors, or the standard deviations. Yeah.
you change that.
Okay.
You point 3 about where
Yeah, it's because he used the X value. Point.
Right.
Then it
Yeah.
allows you to refer, like,
Yeah.
that's where you would say when it goes up by 1%, the number of deaths is 0.33 instead of it goes 100%. 32 per million.
Yeah, so if you mess with if you change the variables like that, you could just double check that the correlation is the same, which it should be. And that's where you know you haven't messed anything up. So the coefficient's going to be different, but it means the same, right? Okay, we'll come back to this. Um, okay, so we did that. Now this was the one that the text part that I just put this in here because I thought it was funny. So I would never recommend making a statement like this, but in fact, regression analysis may be the most widely used statistical technique. So that doesn't mean anything. So that's um, when you say in fact something maybe, it's not a very strong statement. So this is an old textbook, but I thought that was interesting. And so I cut this out. So this is important because general regression equations are valid only over the region of the regressor variables contained in the observed data. So what that means is, let me bring up a little plot of these.
Actually wrote that in one of our answers.
Did you?
Yeah, you, one of our,
Oh yeah, that sounds,
like this is particular to this.
yeah. Okay, so here's the graph for the new x. And so what I mean by that, actually, let me give us variables. So this is um, home, fire, deaths, and this is percentage of smoke detectors. Oops. Okay, so here's our sample of data. And so what that means is if we get data outside of this range, you can't expect this model to predict that. So if we're looking at homes, let's say we go to like um, an area where there's I don't know, maybe you go to like an old area like uh, where there's not as many developed housing and technology. Let's say that area only has 20% of homes with smoke detectors. So this model doesn't have any data points in that range. And so you couldn't use this model to predict that only in this range. So basically from what is this? 50% to like 95% is the only range this is valid to predict. If you get some out of sample observations, you'd have to run the model again, right? Because we don't know what's going to happen if you get down here because we don't have data for it. So that's what that is. Right? Okay. Also, regression analysis is an iterative procedure, and basically, like the quality of the fit is then investigated, and you can modify it or make other adoptions or modifications. And so, normally, when you get a model like this, you would you might check for other variables that affect home deaths if you have data on that, not just smoke detectors. So maybe um, like carbon monoxide detectors might help. Uh, you know, make sure that the flumes are working properly, or if you have other things uh, that can help with home deaths, you might want to put those in the model and modify it. So it's a you, when you get new information, you can add it to the already developed section. Okay, and then this is important, is the regression model doesn't imply a cause-effect relationship between variables. So just because you have a line or a correlation doesn't mean it's a true effect. And I bet if everyone's heard like causation isn't correlation. And if you Google it, you'll get a number of funny images that identify this. Like, so look at like, if you just Google causation is not correlation, you can get something like here we go. The divorce rate in Maine is correlated with the per capita consumption margin. So does that mean that you can predict divorce rates with more margin? Probably not, but that's what the graph shows. So just because you get a correlation doesn't mean it makes sense to interpret it. So you have to make sure that what you're interpreting would come off as an appropriate uh, correlation, or else it's like this, oops, even though this graph is, here's the divorce rate, here's margin, pretty clear they move together, but it's not clear and probably false that either one causes the other, right? Okay. All right. Now, if you looked at this third one, we can calculate the r squared manually as well. So we'll do that. I'm sure we've been excited about this. This one's actually a lot easier because really you're just squaring the correlations. So to get the r squared, it's really not that tricky. Just get the correlation between the two variables and square it, and that's it. So that's the magic there. Okay, so if I go back to this example, and I want to get the r squared, which also should be the same for both, right? 0.82, 0.82. Let's just do it over here. And we'll do it both times just to confirm it's the same. So I'll call this R2 for r squared. Okay, so to get the r squared, we already have the correlation. So all we have to do is take in L2 equals, where's the correlation? Here, squared, raise the 2. Okay, so if you square the correlation, you should get the r squared. Right? That work? Okay, and it should be the same for this range, but we'll do it again. Equals this correlation. Raise the 2 should be the same, 0.82. And if you look at both of the models, the r squared 0.82, 0.82 is not magic either. It's just the square of the correlations. Okay. Now, put that together. Next. Okay. Okay, the third or fourth reading, I can't remember which number, but this one um, showed you that you can also not only calculate the coefficients and intercept, but you can calculate the variance in the standard deviation like before using the trig formulas. So let me show you how to calculate the variance in the standard deviation before we use the equals, Okay. Now, I forgot how to do this, but I know I have an example. Okay, so we need to calculate the deviation from the mean and then the squared deviation from the mean before, okay? So I'm gonna make 2 more columns. And again, this is not required. I'm just kind of showing you the magic behind the formulas. So if I want to calculate the deviation about the mean and the squared deviation for both, we can do that. And this step gets a little cumbersome, so there is a chance I mess this up. Oops. Or still crashes.
You haven't saved it yet?
I didn't, so I must have done some shortcut that I did not want to do. Boy. All right, we might have to stop this here. Huh? No, it's just Excel. Yeah, everything else should be fine. We're still recording. All right, sorry. Let's see if I saved it. I don't know. Yeah, we're good. We got most of it saved. All right. Yeah, that was weird. Okay.
Oh.
S- I think that's what happened. Okay. So if you wanted to follow along, again, you don't have to, but I'm going to manually calculate the standard deviation. Okay. So the first thing you want to do is calculate the deviations of x from the mean, which is just how far x is from the mean of x. All right. We already have the mean of x right there. Okay. So that means that, um, actually, which one do I want to? I want to do this one first. Okay, so the deviation about the mean is equal to x minus the average x, which is 0.84, right? Now, if I lock that cell with a dollar sign, it'll keep it as 0.84. So now I'm gonna subtract all the x's from 0.84 to see how far off they are from the average. Okay, there we go. Now I want to square that because it's part of the standard deviation. So it equals this squared. Okay, and they're not zeros, they're just maybe more decimals. Same thing with y. So deviations about the mean are equals all the y's minus the mean of y. And if I put a dollar sign on the n and a dollar sign on the 2, that'll keep it as the locked mean. Then I can apply that. So that's all the deviations about the mean. And I want to square that. Didn't like that. Okay, and then to get the mean variance and the mean standard deviation, I'll do this. So this works out, it'll be a surprise. Okay, so the variance is the sum of all the square deviations divided by the sample size minus 1. So that would be the sum of this whole range. Oh no. The sum of this range. And then we have 17 observations. So this should be 16. Okay. All right, and then the standard deviation is the square root of the variance. So equals square root of that. Yeah, it works. All right. So you can even go back even further to understand the standard deviation of the variance. So we know what the correlation is. It's just they move together. We know what the mean is, right? And the only thing I think was a bit statistically, like stat properties was the standard deviation. So the standard deviation is the sum of all the deviations from the mean divided by n minus 1, or that's the variance, and then the standard deviation is the square root of the variance. So you can get this, which you can just get with Excel, or you can get this whole thing by just doing the regression, but this is the math behind it. And I could do the same with y. Uh, no, you don't have to, but I guess it's just important to know like what the numbers come from. Yeah, but no, you don't have to. You wouldn't have to show this probably. Yeah. Yeah.
It's just like on the first day where you see like countless
Yeah.
symbols like that at the bottom and then just give you like the
Yeah. No, the whole point is like you could do all this on a graphing paper if you wanted to. It would just take a long time and it would. So it's there's that's what I mean. There's no magic behind this stuff. It's just a lot of yeah. But see how I got the same
yeah.
variance?
Anybody else tell you very well. I'll be honest, I don't work.
Yeah.
But yeah.
Yeah. Okay. Now the last thing I want to show you is how to get the t-stat manually. Um, yeah. So this is well, we're kind of going to cheat here because you can also calculate the standard error, but that I messed up preparing that this morning, so we won't do that. But we can get the t-stat, which is just the coefficient divided by the standard error. That's it. So if you want to get the t-stat that you see in your, outputs here, okay, so here's our t-stat, and you should see standard error right there. So if I want to get that t-stat, it's just equals this formula, the coefficient divided by the standard error. So, sorry, equals the coefficient divided by the standard error should be the same thing. All right. So really, they're just dividing this by this to give you the t-stat. And it's pretty clear that if the coefficient goes up, like if it's a bigger effect, then the t-stat would go up, or if the standard error goes down, it would also go up. So what you're looking for in absolute value is a higher coefficient and a lower error. So if this error goes up a bunch, that could also wipe out your coefficient or your t-stat, because if there's more error going on, it could decrease this. So the two ways to lower your t-stat are decrease the coefficient in absolute value or increase the standard error. Yeah,
Things like by two or
right. So, and you could, I could do the same for this one. The t-stat should be equal to the coefficient, even though it's small, divided by the standard error, which is smaller because we scaled it down, right? So it's not just the size of the coefficient, it's also the smallness of the error, right? Yeah. So it's not the size of the coefficient in the phi, it's the size of the standard error that goes with it. Okay? All right. So one further step, which I might show you next time, is you could also calculate the standard error, which is a bit tricky because you have to get the variation of y from the mean from the line, not the average. So it's basically repeating this instead of using the average, using the predicted from the observation. But I had an example here, but I messed it up earlier, so I won't do
so
that.
you're saying it's off of the trend.
Yeah, right, yeah. I could maybe do it real quick, but let's see, just if I mess it up. So it's basically this. Yeah, this is why it's,
When I was in I don't think it's
really? You calculated this before? I think you guys are, yeah, so here's the standard error. It is 1 over n minus 2 times the sum of the deviations of y from the line divided by the sum of the deviations of x from the line, and both of those are squared. So it's not as complicated as it looks, but we could do it.
it is funny. It is funny that like when you understand what it means, like more simple than how
Yeah.
it looks. Why do they think there's something
I know, when you see these formulas, you're like, what is this? What is this?
that's what some of the information that's all.
Well, that's why I like to start. I like to be like, I like to throw it out there first, and then everyone's like, and then at the date, an hour later, you're like, oh, okay, this is not that.
I mean, you, right? You is me, right?
U is, what are you,
You, right? You call that?
yeah, what?
The U is called you, right? What term?
Where's the U? This one?
No, on the in bracket.
In the bracket? That's a Y. That's a Y, yeah. That's Y, and that's Y hat. Yeah.
Go see.
So Y is the observation, and Y hat is the prediction on the line. Okay. So this is the final. So do you want to do this, or do you want to do it next time? We don't want to do it? Okay. All right. Yeah, we can save this part, but I did want to show you some of the numbers behind the magic. So that was the plan there, is to be able to calculate the coefficients, the t-stats, and the intercepts, and the R square is the easiest, but So if you had to, you should be able to calculate these things without doing the trend line and stuff. But it's once you understand it, you can just do the trend line or the regression.
John, do you do this at work?
No, this part I do like. I mean, these things I don't do. Yeah, but I don't do it manually. No.
Not close enough to graph paper.
But yeah, but well, I mean, people are interested in the t-stats and the coefficients, so yeah, so you're kind of just yeah. No, but a lot of the things I do at work or look at, you're looking at R-squareds, you're looking at t-stats, you're looking at coefficients, you're looking at stuff like that. But no, I'm not going to manually calculate it. But yeah, that's the. But knowing how kind of how it comes about is nice. That's true. Well, it's not just thousands of lines. It's like it maxes out Excel basically because Excel only has 1 million or something, and so well you just don't open it in Excel is the answer. You just it's stored in an Excel data set, but it runs the data through another program. I guess is how it works. But yeah, okay, yeah, like you've never so yeah, if you copy a range that's bigger than the remainder of what's left in Excel, it'll say like error. Because Excel, the standard Excel only gives you this many, so you only get 104 million, or
I don't know.
yeah, actually one little more than 1 million.
That's
What?
like watching the internet. Like, because I didn't know you can go that far.
Yeah, there's also a limit on this way too. You can only go to XFD.
Oh, wow.
See? Yeah, I've never gone that far, but I've gone down far. Never had that many variables, but I've had that many observations. So,
I never even thought of it. Like that's how like to know, right?
yeah,
I never even thought
yeah. Just don't be surprised if one day you're working with a data set that has more than this observations. Well, if you're looking at like 15-minute interval data, then obviously think
yeah,
about
yeah. It makes sense.
Yeah. Yeah.
So program
It'd probably be R. Yeah, yeah. R like it's free to download if you're interested. But this one, and and there's other platforms that go with it. But the one I would use the most is this one called R Studio. Yeah, and so you would upload like a Excel data set and not open it, and then kind of put the commands in here, and then it would do what you want. Right. So you could do all this stuff in here as well, but you would just instead of doing all that stuff, you would just say like reg of whatever variable and it does it for you. There's yeah, yeah.
Is that more efficient?
Definitely more efficient. It's a little more advanced. We could try some of it if you want, but it's up to where the class wants to. This would if we get to time series stuff like a little bit of forecasting, we could use it, but it depends on where we're at.
very important.
Yeah. Well,
Something very
I'll,
important.
I'll try to sneak some in. Excel has its, yeah, it's got its limitations. Yeah. Okay. Should we wrap it up here? All right. Let me just make sure there's no questions. So, no, we got Jordan left and Michael. Okay. So I'm gonna stop the recording for those of you that are, if you're still there. So Jordan and Michael, thanks for joining. I'll upload the video, but I'll see you next Saturday.
Now I'm trapped.